Okay, so a new topic here is Fourier series. And for Fourier series, what we will be dealing with would be periodic functions, right? So that's the first thing that we're going to talk about. Alright, so a simple example of a periodic function is sine x over here, right? And what you want to notice is that your graph of sine x is actually repeating itself, right? Okay, so that's one way you can see that a function is periodic, is that you can graph it, right? And you see that your graph is going to repeat itself um, over certain periods, right? So sine of x has a period of 2 pi, right? And I'll give you a more formal definition of this, right? But sine of x has a period of 2 pi, which means that this piece over here from 0 to pi is just going to keep repeating itself, right? So it'll repeat itself over here between 2 pi and 4 pi, and it will repeat itself on this side over here between minus 2 pi and 0, right? Okay, so sine x is periodic, you can see from the graph, and there are other periodic functions, right? So for example, this function here, right? Okay, the graph, well, at least from your graph over here, you're seeing that this is going to be the graph of a periodic function, right? And the actual periodic function is this function here, right? Now, what this is this summation notation here means that we're going to have 5 terms and you're going to have 5 sinusoidal terms, right? So I can write them out. When n is equal to 1, right, what I will get in this formula is I'll get minus 1 to the 1 plus 1, so minus 1 squared, which is plus 1, and then I'll get 2 on 1, right? So when n is equal to 1, I'll get 2 sine x, right? When n is equal to 2, right, I'll get 2 minus 1 to the 2 plus 1, so this would be negative here. And then I'll get 2 on 2, right? So overall I'll have a 2 here, 2 here, minus 1 over here. So I'll have a minus, and then it will be when n is equal to 2, I have minus sine 2x, right? Okay, so n is equal to 1 gives me a certain sine term. N is equal to 2 gives me a next sine term. Notice here, this is now sine 2x, right? So your frequency over here is actually higher than the sine x, right? And then n is equal to 3 will give me this term over here when I work it out, right? And again, this is again higher frequency, right? So this is, if you want, third harmonic, right? Have a certain coefficient over here, 2/3, right? Okay, and then you're gonna have, so for each n is equal to 1, 2, 3, 4, 5, right? You're gonna have sinusoidal terms, right? So this is the sum of sine terms, right? And notice what you have is that the frequencies are increasing for each of these sine terms, right? Okay, and the graph of this particular function is displayed over here, right? Okay, right, but at least for the time being, this is an example of a periodic function, and this also like the sine x, this also has a period of 2 pi, right? Probably it may not be that clear right now that this has a period of 2 pi, but yeah, both of these have a period of 2 pi, right? Anyway, so both of these are periodic functions, right? Sine of x is periodic. Sine, this function over here, right? The sum of sinusoidals, right? This is also periodic here, right? Okay, and you can see the periodic behavior by looking at the graph, right? But we want a more formal way to see that a function is periodic, right? Okay, so our definition of periodic that we're going to use for this section is that if I have a function, right, and the function is defined for all values of x, so such as the sine x over here, this is defined for all values of x, right? Both positive x and negative x over here, right? A function defined for all x, then the function is called periodic if there is some positive number p such that f of x plus p is equal to f of x, right? Okay, and this small p over here, right, this positive number is an example of a period for your function f of x, right? Okay, so for example, if we consider an sine, right, you well, let's just see that formally that this holds, right, that sine of x plus 2 pi is equal to sine of x, right? Okay, so how can we check this, right? That sine of x plus 2 pi is equal to sine of x, right? Well, what you could do is you just use an addition formula for sine, right? The sine of x plus y is sine x cos y plus cos x sine y, right? And if we use that over here, what we will get is sine x cosine 2 pi times cosine 2 pi plus cosine x times sine 2 pi, right? And you should know that sine of 2 pi is equal to 0, and cosine of 2 pi is equal to cosine of 0, and cosine of 0 is 1, right? So what I have is this term over here where the cosine x will drop off, and all I'm left with is sine x times 1, which is sine x, right? Okay, so I can actually show using this trig identity that sine of x plus 2 pi is equal to sine of x, right? And according to my definition, that means that sine of x is periodic with period 2 pi over here, right? So you want to compare my definition for periodic that I'm going to use to this equation that I have, right? The function is sine of x, and I'm seeing that sine of x plus 2 pi is equal to the original function sine of x, right? Okay, so this is my function x plus p is equal to original function f of x, right? And here it's the same structure, right, where the function is sine, right? And in this case, the small p is equal to 2 pi, right? So this here is an example of satisfying this condition, f of x plus p is equal to f of x, when the p is equal to 2 pi, right? Right, so let's see if we could interpret this equality here graphically, right? So this is my graph of sine x here, right? Okay. Now, what is the graph of sine x plus 2 pi, right? I can get the graph of sine x plus 2 pi from the graph of sine x, right? How I get the graph of sine x plus 2 pi from the graph of sine x is I'll take this graph of sine x and translate it to the left by 2 pi, right? And you want to notice if I translate the graph of sine x by 2 pi to the left, right, this point over here will fall on this point here, right? This vertex over here will fall on this vertex here. This vertex here will fall on this vertex here. This point over here will come to this point, right? In other words, if I take my graph of sine x and translate it by 2 pi to the left, right, the graph would fall back on itself, right? Okay, so translating the graph of sine x by 2 pi to the left gives me the graph of this, right? And from this diagram, you're seeing that you're going to get the same graph. So graphically, what you see in here is that the graph of sine x plus 2 pi is equal to the graph of sine x, right? Because if you, well, one more time, if you take in the graph of sine x and you translate it to the left by 2 pi, it's just going to fall back on itself. Okay, so a little bit of notation. While I did say that the period of a periodic function we're going to denote by small p, right? For the purposes of Fourier series, right, we're going to call the period small p. Instead of calling it small p, we're going to call it 2L, right? And why we're going to do that is that will save us some headaches when we get like the formula for your Fourier series, right? This extra 2 over here comes in handy because then we wouldn't need to have like halves and stuff floating around the place, right? Okay, so for Fourier series, you're going to denote a period as 2L over here, right? Right, and now what I want is, given a function that is periodic with period 2L, right? What I want to do is I want to find its Fourier series, right? And this is what the Fourier series of it is going to look like. The Fourier series would look like, right? Okay, so this is a series over here, right? And it's actually an infinite series starting at n is equal to 1 and going to infinity here, right? You want to remember that you saw a series already, right? So for example, this here is a Maclaurin series for e to the x, right? And you start in from n is equal to 0 over here and you go into infinity. And for n is equal to 0, you'll get a certain term. When n is equal to 1, you'll get x to the 1 on 1 factorial, which would be x. When n is equal to 2, you're going to get x squared on 2 factorial and so on, right? So this index over here, each value in the index gives you a term over here, right? And notice these terms involve extra power over here, right? Okay, so this is a series in x, right? What we have for Fourier series is again a series, right? So again, you have summation. You start in n is equal to 1 over here, right? You go into infinity, but now what you have is it's a series of cosines and sines, right? Okay, so for n is equal to 1, what you're going to get is you're going to get a certain cosine term, right? So when n is equal to 1, you'd have a1 over here, cosine 1 over here, so just pi x on L, right? And then n is equal to 1 will also give you a sine term, b1 sine pi x on L, right? Which is this term over here, right? N is equal to 2 will give you this second cosine term and the second sine term over here, right? Okay, so what you're getting from your Fourier series is you're getting a constant term. This is in your Fourier series, you'd always have your Fourier series is defined using this constant term, and then you have cosine terms and sine terms, right? And you could have possibly an infinite amount of cosine terms and an infinite amount of sine terms, right? And that's similar to the idea of with your Maclaurin, where you have possibly an infinite amount of powers of x adding up over here, right? And in the case of e to the x, you do have an infinite amount of these, right? Okay. Okay, so let me just remind you about something else with your Maclaurin series, right? Now, I have cosine x over here, right? And suppose I want Maclaurin series for cosine x, right? And I know we're going to be doing Fourier series in this section, but this here, hopefully you should remember how to do this, right? Okay, so for your cosine x, if you wanted to get your Maclaurin series, which would be this series over here, it would be a series involving powers of x. Well, how would you do it, right? What you do is you'd use this formula over here, right? Now, this formula is for any function f of x, right? And for any function f of x, this would be a formula for getting your Maclaurin series, right? Your Maclaurin series, the formula for getting the coefficients here. For example, to get the coefficient of the x here, what you need to do is you need to take your function, differentiate it, and evaluate it at 0, right? Okay, so to get Maclaurin series of cosine x, right? Basically what you do is you use this formula over here, where the f of x is cosine x, right? And if I wanted to get the first term over here, the first term is f0. So I put in x is equal to 0, and that would give me cosine of 0, which is this 1 over here, right? Okay, and then to get the coefficient of the x here, that's f prime 0 according to Maclaurin, right? Okay, and well, I need to figure out what the f prime 0 is, right? So for the cosine x, I differentiate to get f prime of x. So here the f of x is cosine x, the f prime x is going to be minus sine x, and I evaluate that at x is equal to 0 to give me minus sine 0, which is 0, right? So that would tell me that for cosine x, the coefficient over here is 0, right? In other words, I'm not going to have a term in x for cosine, right? Okay, the idea, what I want you to get out of this is to get a Maclaurin series of any function, right? What you're doing is you're going to be using some formula over here, right? And the coefficients, right, for the powers of x depend on what your function is, right? So in this case, the function is cosine x. And if, for example, I wanted to get this coefficient, I'd need to use the function cosine x, differentiate it twice, evaluate it at 0, and then divide by 2 factorial, right? Okay, so the idea is for these series like this, right? The coefficients are going to come from the function that is given to you, right? And in this case, the function that is given to you is cosine x, right? And likewise, for Fourier series, right? If I have some function f of x that's given to me, and I want to get the Fourier series of it, your coefficients for your trig functions and the coefficient a0, your constant term, right? You're going to get it using the function that is given to you, right? And how you're going to get it is, well, you have formula for these coefficients in terms of the function, right? And these are the formula for the coefficients, right? In terms of the function that is given, right? That should be given to you, right? Okay, so to get the an, right, to get the coefficient, to get the a0 on 2, and the coefficient of the cosine, right, the cosine terms, right, what you're going to do is you're going to take the function that is given to you, right, you're going to multiply it by this cosine term, right, you're going to integrate it between L and minus L, right, and notice here, this, where the L is coming from is the fact that we going to be taking Fourier series from periodic functions with period 2L, right? So this L over here is coming from the period of your function f of x, right? Okay, and you see why I want to use a 2L over here, right? Because if I didn't have a 2L, then I'd need to start dividing these limits by a half, right? Anyway, right? So to get the an, you have your function f of x that would be given to you. You multiply it against a cosine, you integrate in between L and minus L, right? And then you multiply that by 1 on L, right? And this is a formula for an for a0, so this formula will work for a0 over here, and it'll also work for a1, right? And it'll work for a2, a3, and so on, right? So it works for all n starting from 0, 1, 2, 3 onward, right? Okay, and similarly, there's a formula for bn, right? Again, obtained by integrating f of x, but now you multiply the f of x by a sine, right? And this would be how you'd get your bn using this integral formula here, right? Notice this formula is slightly different because here for the bn, you don't have a b0 term, right? You're going to just have this formula here starts for n is equal to 1, n is equal to 2, 3, so on, right? And you notice here in your formula for your Fourier series, you don't have any b0 term, right? This over here, your b's over here, gonna start at n is equal to 1 here, right? Okay, so this, if you have a function f of x, right? And once I calculate for the given f of x, I calculate the values of an and I calculate the values of bn, right? And I substitute it into this sort of expression. Then with those values, this is going to be a Fourier series for my given function f of x, right? Okay, so just a little bit of notation. These two equations are called Euler formula, right? And the a's, the an's, and the bn's, right, are called Fourier coefficients of your function f of x. Okay, so let's look at an example of calculating a Fourier series, right? I'm given that a function is equal, function f of x is equal to x between minus pi and pi, right? Notice it's your function is equal to x when x is equal to pi, but not equal to x when x is equal to minus pi, right? So you have strict inequality over here, and here you have less than or equal to over here, right? Okay, so this is f of x is equal to x. It's defined between minus pi on pi, right? Okay, and then what you have is you have this second condition over here, right? Now, what this second condition over here is doing for you, right? Remember your definition for a periodic function, right? A function is periodic if f of x plus p is equal to f of x, right? So this part over here is telling you that your function is going to be periodic, and it's also telling you what the period is. It's telling you that the period is 2 pi, right? So for these types of problems, what you'd have is you'd have your function specified first on, this is your starting period over here if you want, or your base period, right? And then what you'd have is this piece over here telling you that the function is periodic, right? Okay, so we want to first sketch the graph of this function here, and then we want to find its Fourier series, right? Okay, so how are we going to sketch the graph, right? Well, what you do is you start with this definition here, right? That f of x is equal to x between minus pi and pi, right? So what you're doing is between minus pi and pi, you're going to sketch your function first, right? So this over here, this illustration is a little better, right? So over here, what I have is, remember, f of x equal to x is a straight line passing through the origin. But I just want f of x being equal to x between minus pi and pi, right? So I just chop off the piece that I need, right? Really, I should have a closed dot over here, and I should have an open dot over here, right? As I have in the notes here, right? Okay, so that's f of x equal to x between minus pi and pi, right? Now, this piece over here is telling you that your function is periodic, right? So the graph, this graph over here is going to repeat every 2 pi, right? So what you want to do is, this is between minus pi and pi, right? So what you want to do is you want to now repeat this graph between pi and 3 pi, right? And when you repeat the graph between pi and 3 pi, you'll get this piece here. Okay, and then you can keep repeating like that, right? And on this side too, it will also repeat, right? So between minus 3 pi and minus pi, your graph is going to repeat, right? So you're going to take this, notice over here between, this is between minus pi and pi, right? So this is between minus pi and pi, minus pi is around there, and pi is over there, right? So you're going to take this part of your graph that is between minus pi and pi, and notice your length from minus pi to pi is 2 pi. You're going to take that and you're going to shift it, right? When you shift it to the left, right, you'll get this piece over here, right? So the basic idea for graphing these is, first you graph on your base period or your starting period between minus pi and pi, and then you, if you want, you just repeat to the right and you repeat to the left, right? And you want to make sure that you put in your open dots and your closed dots appropriately, right? Okay, so that would be how you would graph this here, right? And now what I want to do is I want to get the Fourier series, right? Now I want to get the Fourier series, which means that I need to get these coefficients, the a's over here and the b's here, right? Okay, so the first one that you want to work out is the a0, right? Now your formula for the an here, right? What you want to do is you want to split that into 2 cases, right? You want to split it into the case when n is equal to 0 and when n is equal to 1, 2, 3, so on, right? Okay, so let me start with the a0, and then I will do the case n is equal to 1, 2, 3 onward, right? Okay, and you'll see why I need to split into 2 cases, right? Anyway, so let me start working on the a0, right? Okay, so according to my formula, the a0, okay, so before, well, I need to use this formula here, right? But notice this formula involves L here, right? And the L is coming from the period of your function. So once, if your period is specified as 2L, that would tell you what the L is, right? Okay, so in this case, right, your function is of period 2 pi, right? Okay, so if it's your period is 2 pi, right, then what that means, if you have 2L is equal to 2 pi, right, so this 2L over here is going to be equal to the period of 2 pi here, right? So if 2L is equal to 2 pi, that tells you that the L is going to be equal to pi, right? Okay, right, so I get I know what the big L is, right? The big L is equal to pi, and that comes from the period that is given to me as part of the problem, right? Okay, right, okay, so so I'm working out the case when small n is equal to 0. I know that I'm going to be using this formula when the small n is equal to 0, so let's put in the small n is equal to 0, right? So I'd have a 0 over here, and then I have cosine of 0, right? Now cosine of 0 pi xl, right? This is just going to be cosine, all of this will just turn to 0, so I have cosine of 0, and cosine of 0 is 1, right? So when n is equal to 0, this cosine term is just going to drop off to me as 1, right? And all I'll be left with is the f of x, right? And the f of x between pi and minus pi, right? The f of x. So between pi and minus pi, your function f of x is equal to x, right? So you put that in, right? Or if you want, you could get it, take the information from here, right? Between minus pi and pi, your function is equal to x. So you put that in over here. And now what you have is you just integrate in x between pi and minus pi, and you're going to divide by 1 on pi, right? So remember, you're using your formula 1 on L, integrate in this fraction 1 on L with an integral between L and minus L, right? So the L is equal to pi, so I'm going to have a 1 on pi outside here, and then I'm going to be integrating between pi and minus pi of this x over here, right? And this is not hard integration. You integrate this, you're going to get x squared on 2. And when you put in the pi, you're going to get pi squared on 2. When you put in the minus pi, you're also going to get pi squared on 2. And when you subtract those, you're going to get 0, right? So the a0 over here is just going to turn out to be equal to 0. Okay, so we get one value for my Fourier series, right? We know that the a0 is going to be equal to 0, right? Okay, and now let's start working on the an when n is equal to 1, 2, 3, so on, right? Okay, so again we're going to be using this formula, right? And again we're going to be using the fact that the L is equal to pi, and we're going to be again using the fact that f of x is equal to x in this case, right? The f of x is equal to x. Okay, so let's work on getting the an. Right, when n is equal to 1, 2 onward, right? Okay, so the function f of x is equal to x, the L is equal to pi, right? So I'm integrating between pi and minus pi, right? The L is equal to pi, so notice I have cosine n pi x on L over here, right? So when I put in the L is equal to pi, this pi will cancel with this pi, and I'm just left with cos nx here, right? Okay, so when I put in the information for the L, right, that the L is equal to pi, and I put in what the function is equal to x, right? And I simplify it, right? Then I get this integral, right? Now, you want to notice something over here, right? So this is in the case when n is equal to 1, 2 onward, right? In the case of when the n was equal to 0, right, what happened, right? In the case n is equal to 0, what you had was cosine of if the n was equal to 0, you had cosine of 0 over here, and then the cosine term just dropped off as 1, right? But in this case, because n is equal to 1, 2 onward, right, this cosine is not going to drop off, right? Matter of fact, it just simplifies down to cosine n of x, right? And now you have x times n cosine nx over here, and I need to integrate this, right? So the integral in the case of an when n is equal to 1, 2 onward, right? This integral over here is vastly different from the integral from a0 here, right? So in the integral for a0, you're not going to have any cosine term, but for the integral for the an, you will have a cosine term in it. And this makes the method of evaluation for the integrals different, right? Here, this was straightforward, right? But here, you'd need to do a little work here to integrate this by parts, right? Alright, so let's do the integration by parts, right? So, using the formula, that integral of v du is going to be uv minus integral of u dv, right? Okay, so I choose the v and the du, right? And I choose the v because I'm going to differentiate the v, right? And I want to get rid of this x over here, right? So I choose the v to be equal to x. When I differentiate the x, I'm going to get 1, right? So the dv is going to be 1 dx, right? And then the du, if I choose the v to be equal to x, the du will have to be everything else, right? Okay, and here, once I have this du, in order to get du, I integrate, right? And if I integrate cos nx, right, I'm gonna get sine nx on n, right? Okay, so now I just use my integration by parts formula. I have uv, so this is x times the sine nx on n. Okay, I'm gonna evaluate that between pi and minus pi. Remember, I had this 1 on pi outside to start off with, right? So I had this 1 on pi outside over here, right? And then the integral of u dv, right? So that's the integral of sine nx on n times 1 here, right? And again, I have that 1 on pi from over here with the minus sign that's coming from the integration by parts formula, right? Okay, and I need to integrate this. Integral of the sine is going to be minus cosine, and that minus will hit this minus to give me a plus, right? And when I integrate the sine, I will get this extra n coming down over here to give me the n squared, right? Okay, so after the integration, I will have this here, right? And I still need to put in the pi and minus pi, right? So I put in the pi over here. I'm going to get pi sine n pi on n, right? And over here, when I put in the x is equal to minus pi, right? I'm going to have, right, a minus pi here, sine minus n pi on n here. So the minus pi sine minus n pi on n, right? And I'm subtracting that one, so that's the subtraction over here, right? Okay, so for some reason I decided this x is equal to minus pi. I wrote it on this side, and for this x, when the x is equal to minus pi into this cosine, I wrote it on this side, probably just because both of those are negative, and I'm collecting the negative signs as I go along, right? Anyway, so when the x is equal to pi, I get this term. When the x is equal to minus pi, I get this term. When the x is equal to pi over here for this cosine on n squared, I get this term here. And when the x is equal to minus pi, I get this term over here, right? Okay, now one thing you want to note over here is I have this sine n pi and cosine n pi, sine minus n pi and cosine of minus n pi. Alright, so we need to figure out what this sine n pi is and what this cosine n pi is, right? Okay, so let's just recall some values for cosine of an angle, right? And by pi over here, remember pi is 180 degrees, right? So 2 pi is 360 degrees, and minus pi over here is minus 180 degrees. Okay, so you all know that cosine of 0 is 1, right? And then cosine of 180 degrees is minus 1, right? And if you have cosine of 2 pi, right? Well, cosine of 2 pi is the same as cosine of 0, right? So that's going to be equal to 1, right? And I can keep going like that, right? Cosine of 3 pi is going to be equal to minus 1, right? Because, well, the values of cosine, it's periodic, right? So cosine pi plus 2 pi is going to be the same as cosine of pi, right? Anyway, so cosine of 3 pi would be minus 1, and cosine of 4 pi would be 1, right? So what you want to notice over here is that the values of cosine, if it's 0, pi, 2 pi, and so on, what it's doing is oscillating between 1 and minus 1, right? And how you can write that is using this formula over here, right? And you can check, right? If I put in small n is equal to 1, I get cosine of pi is minus 1 to the power 1, which is minus 1, right? Okay, so this over here, this expression cosine n pi is equal to minus 1 to the n, right? That explains this sort of oscillating behavior between 1 and minus 1, right? And then for the values of sine, it's easier, right? Because, well, sine of 0 is 0. Sine of 180 degrees is 0. Sine of 360 degrees is 0. Sine of minus 180 degrees is 0, right? So sine of n pi is equal to 0, right? When n is an integer, right? When n is 1, 2, minus 1, minus 2, and so on, right? Okay, so I get that, right? And now also, well, what about cosine of n minus n pi, right? Well, what you want to do is you want to use this trig identity that cosine of minus of the angle is equal to just cosine of the angle, right? So what that means is that cosine of minus n pi is just the same as cosine of n pi, which is minus 1 to the n, right? and sine of minus x is equal to minus sine x, and I can use that over here, right? So sine of minus n pi is minus sine n pi, but this is just 0 anyway, right? So it's just minus of 0, which is just 0, right? Okay, so I get these four formula, if you want, right? And these are very useful when you working out Fourier series, right? Because your endpoints would pretty much always give you expressions like these, right? Okay, and you've seen it over here, right? Here I have sine n pi, here I have cosine n pi, sine minus n pi, and cosine minus n pi. So I have these here, right? So, well, we just saw, right, and it's also summarized in the notes here, that the sine terms are just going to drop to 0, right? So all I'm left with is just the cosine n pi on n squared, right? And this is minus 1 to the n on n squared. So that's this one over here. Okay, and this also is minus 1 to the n on n squared, right? Okay, now what you want to notice is that this expression over here, minus 1 on n squared, is the same as this, and I'm subtracting both of them, right? Okay, so if I subtract identical things, I'm going to get 0 here, right? So I get an is equal to 1 on pi times 0, which is just 0, right? And it's for values of n from 1, 2, 3 onward, right? So for the positive integers, right? Okay, so what I get is that an is equal to 0 for n is equal to 1, 2, 3, so on, right? And you want to recall what I have for the a0, right? For the a0, I also got that the a0 is 0, right? So what that is telling me in this particular Fourier series is that the a0 and the an's are all going to be equal to 0, right? So the Fourier series that I'm going to get will just involve sine terms, right? Okay, so I still need to calculate the bn. Alright, so to get the bn, we're going to use Euler formula, right? But I guess the version for bn now, right? Right, so we know from before that the L is equal to pi. Your function is going to be equal to x between pi and minus pi. And now what I'm doing is I'm integrating x times sine, right? The L is equal to pi inside your sine over here, so this pi will cancel with this pi. So I'm going to end up integrating x sine nx between pi and minus pi, right? Multiplying by 1 on pi. Now your method of evaluation over here again is going to be integration by parts. Again, I'm just going to choose the v to be equal to x, and then the du is now sine nx dx, right? Okay, so this is just integration by parts. What I'm going to have is, when I do my integration by parts, I'm going to have uv, which is this minus x cos nx on n, right? Then I'm going to have u dv, right, which is minus cos nx on n times 1, right? So that's the u dv over here, right? This minus minus will give me a plus, right? And I need to integrate this cos nx on n, right? And when I integrate the cos, I will get sine, and I need to divide by the n inside, so I'm going to get an extra n down here for the n squared, right? Okay, so far I have this. Remember, I had the 1 on pi outside over here, so I also have the 1 on pi outside over here. And again, what you do is you put in your pi and minus pi in here and in for the sine, right? When you put in the pi over here, you're going to get x cos n pi, right? Minus pi cos n pi on n, right? And when I put in the minus pi over here, I'm going to get minus cos minus n pi with a minus over here, minus pi, and with a next minus here, right? And when I put in the pi in for the sine nx over here, I'm going to get sine n pi on n squared here, right? And when I put in the minus pi, I'm going to get sine minus n pi on n squared here, right? Okay, so as we saw before, right, the sine n pi is just going to sine of n pi and sine of minus n pi is just going to drop off for me, right? What I'm left with is the cosine of the n pi, and the cosine of n pi is minus 1 to the n. The cosine of the minus n pi is minus 1 to the n. Okay, and let's see what I have now, right? Well, I have minus pi minus 1 to the n on n, right? And here I have right, so I have 3 minus signs over here, right? So this is minus, 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 right? So overall this is going to be minus pi minus 1 to the n on n, right? Okay, and I have it over here. So I have two quantities over here of the same sign, so I'm just going to have twice that quantity, right? So that's where this 2 comes from. And this pi on the outside over here, on the outside in the denominator here, is going to cancel with the pi on top here, right? And the pi on top here. So the bn would work out to be minus 2 to the minus 1 to the power n divided by n, right? So this is my bn over here, right? Okay, so now in my for my Fourier series, this is the form of the Fourier series. Remember that the L is going to be equal to pi, right? I figured out that the A is all 0, right? So the A0 is equal to 0 and the AN is equal to 0. So I'm not going to have this constant term and I'm not going to have cosine terms, right? All I'm going to be left with is sine terms here, right? So that's why I just have a sine terms over here. The L is equal to pi, so this pi in the denominator will cancel with the pi in the numerator, so I have the sine nx. And then finally I put in what the bn is, right? The bn is 2 to the minus 1 to the n plus 1 on n, right? So I put that in over here, right? So again, the a n is just equal to 0. We worked out that for all values of n. The a0 is equal to 0, right? So that means that cosine term dropped off, constant term dropped out. So all I have in this Fourier series would just be the bn with the sine, right? And I put in the bn over here. And I just simply clean this up a little bit because the L was equal to pi and I got sine nx here, right? Okay, so this is the Fourier series of my given function, right? So this function given by this graph, so the function specified here and displayed by this graph, this is its Fourier series. The Fourier series that I obtained was this infinite series here, right? Now what I'm going to do is I'm going to look at not the entire series here, I'm going to look at the first few terms of the series, right? Okay, so over here what I do is I look at the first 5 terms of the series and I wrote them out, right? Okay, so this here, these first 5 terms, this is an approximation of your Fourier series here. Now, this Fourier series, the point is that the Fourier series, it's this here is, this function is essentially the same as the function that was given to me, which is this function over here, right? With some exceptions because of the discontinuities and so, right? But the idea is that at a sort of basic level that your Fourier series here, right? This Fourier series that we got is really the same as this function here, right? Except possibly at a couple points, right? Okay, so that's when I have the when I use all terms in the Fourier series, when I consider the infinite series, right? But if I don't consider the infinite series, right, and I just take some of the terms, right, if I just take some of the terms from the Fourier series, what I do is I get an approximation to my original function, right? So, and it's shown in the notes, right? So this is the Fourier series that I got, right? And if I take, for example, the first 5 terms from this Fourier series and I graph it, this would be what I would have, right? Okay, so I get something that looks somewhat like the the graph that I had, right? Okay, so this is the graph that I had, right? Okay, and this looks like it, right? You have these sloping edges over here, right? Okay, so this is when I use 5 terms, right? Now, if I use more terms, right? If I use, for example, if I use 25 terms, right? This would be what I would get, right? And you notice that the approximation is starting to get better, right? You still, however, have a big difference because you have discontinuities in your original function, right? But you see, the thing is, this function here is a sum of sine functions, right? And the sine functions are continuous, which means that if this is going to be a sum of sine functions, it will have to be continuous, which would mean that this your top vertex over here has to join to this bottom over here, right? Unlike what happens in the original function, right? But the key thing is the approximation is the same in the sense that, for example, between minus pi and pi, this part here between minus pi and pi is essentially the same as the part between minus pi and pi, right? Okay, and when I take even more terms, so this is when I'm using 25 of the terms from my original Fourier series, right? So when I use 5, I had this rough approximation. When I use 25 terms, I got a better approximation. And if I use, say, 1,000 terms, right, from the Fourier series, right? In other words, I'm taking 1,000 of these terms from your from this Fourier series over here. If I'm taking from n is equal to 1 to 1,000, right, I get a pretty good approximation of my original function. In particular, between minus pi and pi over here, it's a straight line, and over here, between minus pi and pi, it's essentially a straight line, right? So the idea is that the more terms you use from your Fourier series, the better your approximation is going to be, right? And we can see a next example of this, right, in this graphic here, right? Okay, so here, this is just using 2 terms, right? And if you use 3 terms, you get a better approximation. 4, you get better. 5, 6, 7, 8, 9, 10, 11, 12, right? Okay, so the more terms you use, the better your approximation is going to be, right? This is just 12, right? So you still have this sort of jagged behavior between minus pi and pi, right? If you use 1,000 terms, right? So okay, so notice over here, what you're doing is you're using this is the sum of the first 12 sinusoidal terms, right? Okay, well, first 12, but the first one, the A0 is 0, right? Okay, and the first 11 of these sinusoidal terms gives me a fairly decent approximation. But if I use 1,000 of the sinusoidal terms, I would get a very good approximation, right? Okay, so that's one thing that your Fourier series will do for you, right? The terms from your Fourier series, right? When you add them up and you add up a certain amount of them, the first, say, for example, the first 12 of them, you'd get an approximation of your original function, right? Okay, and the more terms you add, the better your approximation is going to be, right? So this is one application of a Fourier series. One application of your Fourier series is that you use it to approximate your original function, right? Which in this case was this original function, right? Now, why you'd want to do that is because notice this function now is expressed in terms of sines, and sines are particularly easy to, say, integrate and differentiate and so on, right? So if you're solving certain problems and for example, with partial differential equations, and so this sort of sinusoidal expansion comes in pretty handy for calculations, right? So a next application of your Fourier series would be, say, to identify the relative strength of your high and low frequencies in a signal, right? Okay, so if, for example, some signal or some function, we can get the Fourier series of it, right? Now, with the Fourier series, what you want to notice is that, say, I have this cosine term pi x on L, and I have a corresponding sine term pi x on L, right? Then I have a cosine 2 pi x on L and a corresponding 2 pi x on L, right? So what I can do is I can group those corresponding terms, right, using a little bit of trigonometry. So you're probably familiar with this, that if I have a cos theta plus b sine theta, I can write this as just cosine theta with a phase shift and some the magnitude over here, and the magnitude is equal to the square root of a squared plus b squared, right? Okay, so this sort of trig identity allows me to write this Fourier series in what's called harmonic form, right? Okay, so what I'm doing is I'm grouping the cosines and sines, right, into a single cosine over here that's representing the frequencies, right? Okay, and the idea now is that well, when n is equal to 1, right, what I have is the fundamental, right, and then when n is equal to 2, I have second harmonic. N is equal to 3, I'm going to get the third harmonic out of this, right? And the thing is, now what you can do is you can look at these values of the big C here, right? For example, the C0 and the Cn, to give you an idea of the amplitudes of the different harmonics, right? And seeing the amplitudes of the different harmonics will in fact tell you, well, do you have, say, like low frequencies, or do you have more high frequencies, and so on, right? Right, so let's recall that this is, we obtained this from the Fourier series of your function f of x, which was this function here, right? So this function, we got the Fourier series, and then we took the first 25 terms of your Fourier series, right? And the graph of it looked like this. And this is a this is roughly a sawtooth wave, right? Now with this here, right, using the Fourier series, what you can do is you can identify the frequencies and the amplitudes of the frequencies, right? And this is done here, right? In this picture, you see in that, well, okay, this is the sawtooth here, and what these values are indicating is these are indicating the relative size of the amplitudes of the harmonics, right? Okay, so this one over here, this is representing the this amplitude of C1 of your first harmonic. This one is representing the amplitude of the second harmonic, and you see that the amplitudes are decaying, right? So this is giving you an idea that the frequencies in the sawtooth is more concentrated at for your lower frequencies in the lower harmonics here, right? Right, and this sawtooth wave has a certain sound associated to it, which is not very pleasant, but we're going to compare it to a next periodic signal in a second, right? Okay, so this periodic signal, we could also get your Fourier series for it, right? And then with the Fourier series, we could write it in harmonics form, right? So we could actually compare the magnitudes for the various harmonics. And in this particular one, this has two harmonics right next to each other, right? So basically what this is this is sum of two cosines of just slightly different frequencies, right? If you have two cosines of just slightly different frequencies, and you see this, so this over here is indicating that that to start off with, your fundamental has 0 amplitude, so it isn't there. First harmonic isn't there, right? It's only the only frequencies showing up here are these two ones, that are next to each other, right? Okay, so I have these two frequencies that are next to each other, right? And this sort of situation is called a beat in acoustics. What you have is you have the sum of two sinusoids of slightly different frequencies, right? And once you have that, you're gonna have a certain sort of interference pattern like this, right? And sound of this isn't too bad. Okay, but the point is that I want to make is this periodic signal over here. We can actually identify what the frequencies are, right, by using Fourier series, right? And well, this is the form of the Fourier series that we're gonna use to identify, right, the frequencies, right? Okay, so this over here, this is an application of Fourier series, right, to give you an idea of the frequencies in a signal, right? This is outside the scope of the class, right? What I really expect you to do is for a given function to actually just determine its Fourier series. So let's talk a little bit about even and odd functions, right? Okay, so I have this function which is f of x is equal to x plus 1, right? The graph of it is a straight line through the origin with intercept 1 here, right? So this is f of x, right? Now what is f of minus x, right? So again, this is f of x is equal to x plus 1, right? Well, how you get your graph of f of minus x, right, is you reflect the graph of your original function f of x in your y-axis, right? So f of minus x is the reflection of your original graph in your y-axis here, right? Okay, so that's f of minus x, and if I want to get minus f of minus x, right, to get minus f of minus x, okay, what I do is I have the graph of my original function. First I form f of minus x, which is the reflection in the y-axis. And to get minus f of minus x, what I'm going to do is I'm going to take this red graph here and I'm going to reflect it now in the x-axis. Alright, so this is minus f of minus x, right? Okay. Okay, so let's consider your function f of x is equal to x squared, right? Now for your function f of x equal to x squared, if I now consider f of minus x, right? Now you want to notice f of x equal to x squared, this graph over here is symmetric about your y-axis, right? So if I reflect this graph in the y-axis, right, this piece will go to this piece will go to this piece. So I should get back the same thing, right? So what I'm saying is the f of minus x, which I just said you form by reflecting in the y-axis, I should actually just get the same graph, right? And you can see it here, right, in this graphic, right, that this is your f of minus x, right? The original function was this yellow, has this yellow graph over here, and the f of minus x, this new function here, well, it's actually the same function, right? So that over here for your function f of x is equal to x squared, right? This is an example of an even function, right? An even function graphically, when you reflect it in the y-axis, you're going to get back the same function, right? Okay, so let's consider f of x is equal to x cubed, right? Now, f of x equal to x cubed, you probably see here that if I reflect in the y-axis, in other words, if I form f of minus x, I do not get the same graph, right? So this is f of x equal to x cubed. This yellow graph here is the graph of f of x equal to x cubed. And f of minus x is I will get by reflecting in the y-axis. Okay, and you notice I don't get the same graph, right? Okay, so what that is telling me, at least graphically, is that f of x equal to x cubed is not an even function, right? If it were an even function, when I reflected the graph in the y-axis, right, I would get back the same graph. And in this case, I do not get back the same graph, right? So f of x equal to x cubed is not an even function, right? However, okay, so let's look at our definition of even and odd function, right? A function is said to be even if f of minus x is equal to f of x, right? In other words, if I have a function, right, and I consider its graph, right, and f of minus x, the graph of that would be, I'd get that by reflecting in the y-axis. If when I reflect in the y-axis I get the same function, right, then this function f of x is said to be even, right? Or you could really define it in terms of the functions that function is even if f of minus x is equal to f of x, right? And an example of an even function is f of x is equal to x squared, right? Because this is the function x squared, and the red graph over here, this is f of minus x, and what you want to notice is that in this case f of minus x is equal to f of x, right? Okay, so graphically we see in that f of x equal to x squared. This is an even function. Alright, and now we have a definition of a odd function, right? Function is odd if f of minus x is equal to minus f of x, right? Or in other words, f of x is equal to minus f of minus x, right? And so function is odd if f of minus x is equal to minus f of x, right? So I have it written here, right? But of course I could always just move this minus sign onto the left hand side. So the condition for a function to be odd is that minus f of minus x is equal to f of x, right? Okay, so let's see an example of a function that's odd, right? Okay, an easy example of a function that is odd is f of x equal to x cubed. Right, so this is my original function f of x, right? Notice f of minus x is not the same as the original function, right? So that is telling you that the x cubed, f of x equal to x cubed, is not even, right? But if, however, I look at minus f of minus x, right, I actually get back the same graph, right? Okay, so this is the original f of x equal to x cubed, and this is when I form minus f of minus x, right? Okay, and how you form minus f of minus x is you can start with the f of minus x and then reflect that in your y-axis. Right? You reflect it in your x-axis, and when you reflect it in your x-axis, okay, so if you have your f of minus x and you reflect it in your x-axis, you would get minus f of minus x, right? And the point is that I want to make here is that this is f of x equal to x cubed, and minus f of minus x is in fact the same function, right? So an example of a function that is odd, right? Example of a function that satisfies f of minus x is minus f of x is when f of x is equal to x cubed, right? And we can check the work in here, right? So this is done in this example. This is looking at it graphically, but you can actually work it out. And most of the times, what I'd expect you to do is when you're doing your Fourier series questions, if you want to determine if a function is even or odd, right? Really, you should graph it and check to see if it's even or odd, right? So it's even if it's symmetric about the y-axis, and it's odd if when you reflect in the y-axis and then you reflect in the x-axis, you get back the same graph. Or a next way to look at this is if you rotate this about 180 degrees about the origin, right? A next way graphically to see if a function is odd is if you rotate the graph function 180 degrees about the origin. You get back the same graph, right? Okay, so you see in that example that x cubed is odd, right? Anyway, but I can check using my definition here, right? So I have f of x is equal to x cubed, right? So what I'm going to do is I'm going to calculate f of minus x, right? So if f of x is equal to x cubed, to get f of minus x, wherever I see x in this expression, I'm going to replace by minus x. So I get f of minus x is minus x cubed, right? and minus x all to be cubed is minus x cubed, right? So I see that f of minus x is minus x cubed, right? Right, okay, and now what I consider is, notice that f of x is equal to x cubed, right? So what I see is that the f of minus x, which is equal to minus x cubed, and x cubed is equal to f of x, what I get is f of minus x is equal to minus f of x, right? Okay, so that is a way of checking. The next way of checking that is not graphical, that this function is an odd function, right? And we can check also using this definition here if a function is even, right? So we want to check to see that this g of x is equal to x to the fourth is even, right? Okay, and what we do is, remember, these definitions here hinge about taking your function and inserting minus x into it, right? So I have, this is my function, g of x is equal to x to the fourth. I construct g of minus x, and how I get g of minus x is in this expression. Everywhere I see x, I'm going to replace by minus x. So here I have minus x to the fourth, which is just x to the fourth, right? And here I see that g of minus x is x to the fourth. But that's just the same as my original function, which is g of x, right? So you see the x to the fourth is g of x. So what I get is g of minus x is equal to g of x. And therefore, the function g of x over here satisfies this. So g of x is an even function, right? Okay, and you can check in this part 3 over here, right, that this particular function is neither even or odd, right? So while some functions are odd and some functions are even, some functions are neither even nor odd, right? And I will do this one graphically, and you check in the notes to how to actually work it out, right? Okay, so this is my function x cubed plus x to the fourth, right? Right. So this is the graph of my original function. This is not symmetrical about your y-axis, right? And when you form your f of minus x, which will reflect in your y-axis, you don't actually get back the same thing, right? So you're seeing that f of x is not equal to f of minus x, so your function is not an even function, right? And when you form the minus f of minus x, right, you see that the graph of minus f of minus x is not the same as f of x, and that tells you that your function x cubed plus x fourth is also not odd, right? So it's neither even nor odd. So why we care about the even and odd functions is that it makes our calculations, if we know that the function is, say, odd beforehand, right, then it'll make our calculations easier, right? So remember, if I have when we find in Fourier series, right? Okay, so if I have a function f x over here, remember this is the form of your Fourier series. You needed to get your coefficients an, right? And you needed to get your coefficients bn, right? And we saw that getting the an and bn, it's a fair amount of work with the integration, right? Okay, but if we know that, for example, that the function beforehand is odd, right? Then if your function is odd to start off with, right, then what this result is saying is that the a's are just automatically 0, right? So if you know that the function is odd beforehand, then the a's are just going to be automatically 0, which means that you wouldn't need to work out this integral over here. All you need to do is you just need to calculate the bn, right? And the example that we just did, right, for this function f of x is equal to x, right? When we're doing these calculations, what we're doing is we're just integrating from minus pi to pi, right? We're integrating from L to minus L. So we just really just integrating on this piece over here. So if we want to check to see if it's even or odd, all we need to do is we just need to check on this base period over here, right? Now this function is just f of x is equal to x, right? And f of x is equal to x. you should realize that f of x equal to x is actually an odd function, right? Okay, and I'll just do it over here. So this is f of x is equal to x, right? F of x equal to x is not even, right? Because if you reflect in the y-axis, you don't get back the same graph. But if, however, if you rotate it 180 degrees about the origin, right, or you reflect in the y-axis and you reflect in the x-axis, you'd get back the same graph, right? Okay, so you see in graphically here that f of x equal to x is actually an odd function, right? Okay, so what that would mean when we were doing these calculations, if we knew beforehand or if we checked beforehand that your function was odd, right? You didn't need to do all this integration here, right, for the a's, right? We just know from beforehand that the a's were just going to be equal to 0, and in order to work out the Fourier series, all we need to do is we just need to work out the bn, right? Okay, so if you have an odd function, your Fourier series is all the a's are going to be equal to 0. Right, so all a's are going to be equal to 0, and if all the a's are equal to 0, right, you have no constant term, and then you're not going to have a cosine term, and all you'd be left with is sine terms, right? And that is what this is saying over here, right? You have an odd function, the a's are 0, and which means that your Fourier series is just going to take the form of just having sine terms only, right? And that is what it worked out for this example. This was odd function, and notice what we got was a Fourier series with just sine terms in it alone, right? This is what we got for answer. Okay, so this is an example of a function f of x that was odd, and this was the Fourier series just containing sine terms alone. Okay, and similarly, if a function is even, right, if a function is even, then the b's are just going to be 0, right? So if the function is even, the b's are going to drop off for you, and all you'd be left with is a constant term and cosine terms, right? Okay, so if you have an even function, right, then the bn's are going to be equal to 0, and therefore your Fourier series is going to take this form here, right? Notice this form here as compared to this form. This form does not have any sine terms, doesn't have these sine terms in it, right? Okay, so the point about this is if we calculate in a Fourier series, and it's a good idea to check beforehand that whether your function is even or odd, right? And if you could determine if it's one of those, right, then what you do is you'd save yourself a certain amount of work, right? Okay, so let's see an example of calculating. Let's consider this function, right, which is f of x is equal to 1 minus x squared, right, between minus 1 and 1, and f of x plus 2 is equal to f of x, right? So they ask us to sketch the graph and then find the Fourier series, right? Okay, so if you're going to sketch a graph of this function, what you do is, as in the case of the previous example, you sketch on your base period over here, right? So from minus 1 to 1, right? And 1 minus x squared is an inverted parabola with a y-intercept of 1, right? So this piece between minus 1 and 1 is 1 minus x squared, right? And this part, f of x plus 2 is equal to f of x, is telling you that your function is periodic with period 2, right? Now notice the length of your base period was from minus 1 to 1, so your length over here is 2, right? In other words, your period 2L is equal to 2, right? So in order to graph this function, what you do is you first draw your inverted parabola here between minus 1 and 1, and then you just keep repeating that, right? Okay, so that would be a graph of your function. And to determine if this is even or odd, right, well, what you should do is just look at it and look for any symmetry. And clearly this graph is symmetrical about your y-axis, right? If you reflect in your y-axis, right, the graph would fall back on itself, right? So this is an even function, right? And for this even function, the b's are just going to be equal to 0, right? So because the b's are going to be equal to 0, your Fourier series is just going to take this form over here, right? So let's actually calculate, right, what the Fourier series is. Okay, so what I would need is the period, right? The period 2L is equal to 2, which is specified over here. So that is going to tell me that the L is equal to 1, right? Okay, so this is the form of my Fourier series, but I still need to calculate the A's and the B's, right? Sorry, I still need to calculate the A's. I do not need to calculate the B's. I just need to calculate A0 and AN, right? Okay, so to calculate the AN, the A0 and the AN, what I will use is I use my Euler formula for AN here, right? So this is the formula that I'm going to use to calculate the AN. And remember, you want to split this into cases when the n is equal, small n is equal to 0, and then the other cases n is equal to 1, 2, 3, so on, right? Okay, so first we calculate the A0, right? Using this formula, when the small n is equal to 0, when the small n is equal to 0, I get cosine of 0, and cosine of 0 is equal to 1. So the cosine will drop off for me. Remember, I said that the big L is equal to 1. So what I have is just the integral of 1 minus x squared between 1 and minus 1, and that's not hard. This will give me 4 and 3, right? And okay, and the function that I'm integrating between 1 and minus 1 is this function that was given to me over here, this 1 minus x squared, right? And now I consider the second case for the ANs, right, when the small n is 1, 2, 3 onward, right? Okay, so using my Euler formula here again, right, the function is 1 minus x squared times the cosine. The L is equal to 1 here, right? So I put that in, and the big L is equal to 1 here and here, and here as well, right? So I put it in, and what I have over here is I have an integration where I need to do this integration by parts, right? Okay, so integration by parts, well, here you need to, when you're doing your integration by parts, what you're going to do is you're going to choose, you need to choose your v, which you're going to differentiate, and then everything else is going to be the du, right? And you choose the v to be 1 minus x squared, because what you want to do is you want this 1 minus x squared to simplify down to basically this 2x here, right? Okay, so I choose v is equal to 1 minus x squared. The du is equal to the cos n pi x dx, right? Differentiate to get the dv, and integrate here to get the u, right? And here I just use the uv, right? And minus the integral of u dv, which is this here, right? Nice thing here is when I put in 1 and minus 1, if I put 1 into this, I'm going to get 1 minus 1 squared, which is just 0, right? And 0 times this expression would be 0. And when I put minus 1 into this expression, I get 1 minus 1 squared, which is 1. So I get 1 minus 1 again, which is also 0, right? So this term drops off, and all I'm left with is just the integration here, right? This minus minus gives me a plus. So I have the integral 2x sine n pi x on n pi, right? Now notice here, this I need to use integration by parts again, right? And this hopefully you should be familiar with, right? If I have, say, a polynomial and x squared here against a cosine or a sine, right? In order to work this out by parts, I need to use integration by parts twice, right? Okay, so I'd use integration by parts once to get me down to this 2x sine n pi x over here on n pi, right? And now I need to use it again. I choose the v is equal to 2x, right? Because I want to simplify that. Everything else is going to be the du, right? And I just use my integration by parts formula, right? This is uv over here, and this is u dv over here, right? Okay, and here I need to integrate this, right? When I integrate the cosine, I will get sine, and I need to divide by the coefficient here, which is n pi. So the n pi would hit the n squared pi squared to give me an n cubed pi cubed. Right, this minus minus would be a plus, and right, and when I integrate cosine, I get plus sine here, right? Okay, and now I put in my values, which would be 1 and minus 1, right? Now when I put in the right, when I put in the 1, I will get 2 cosine n pi here on n squared pi squared, right? Okay, so minus 2 cosine n pi on n squared pi squared, which is this term, right? Then I put in the x is equal to minus 1, which gives me minus 2 minus 1 cosine minus n pi on n squared pi squared, right? And then here I put in the 1 to get me 2 sine n pi on the n cubed pi cubed, and I put in the minus 1, right? Notice I have sine n pi, sine minus n pi, cos n pi, and cos minus n pi, right? And as in the previous example, right? Right. So whenever you're working out your Fourier series, right? You usually will see these here, right? And the nice thing is the sine n pi and the sine n pi and the sine of minus n pi, those are both equal to 0, right? So these drop off for me, and all I'm left with is the cos n pi, right? Okay, so the cos n pi is minus 1 to the n. This is 3 minuses over here, so overall this is a minus. So the sign of this expression is the same as the sign of this expression. Okay, so I'm going to get twice this here, right, which is going to give me 2 times 2, which is 4, right? So I get 4 minus 1 to the n on n squared pi squared, which is this here, right? Okay, so my Fourier series, right, for Fourier series for my even function is going to take this form, right? I worked out what the a0 was, right? The a0 was 4 on 3, right? I worked out what the an is, right? So all I need to do now is just put in what the a0 is and put in what the an is and put in what the L is. The L is equal to 1, right? Okay, and when I do that, I get my answer for my Fourier series, right? I notice this just has a constant term and cosine term in it, right? It doesn't have any sine term. And why it's in this form is because the function f of x was an even function.